All right, so hello everyone to another session of Open Neuromorphic workshops. So some of you actually might recall or have seen maybe a blog post about benchmarking SNN frameworks, and started off with some of the most popular ones in terms of latency benchmarks, in terms of memory benchmarks. Then all along came a new contestant, namely Spyx, and blew the competition out of the water, pretty much. So it's great pleasure to have Kate here today to talk to us about Spyx, his new framework. All right, I will disable this one. How you doing, man?
Good. Glad to be here.
Cool. Where are you now at the moment, actually?
So currently I'm at the University of Cambridge doing the machine learning MPhil there. Last year I was at the University of Sussex working on spiking neural networks, and that's kind of where this project was born out of. So really happy and
Super
excited
nice.
to share it.
So how long have you been working on SNNs or like neuromorphic roughly?
Oh, SNNs really only the last 8 months or so. I learned
That's some serious
JAX.
progress, man.
I mean, I'm following in the footsteps of a lot of people who really blazed the trail, like Jason with SNN Torch and Jens with Norse. Their documentation
Super
and tutorials really laid the groundwork, and I just brought in some JAX tooling, and that's how we got here. So
cool. Well, with that, I will let you take the stage, and please give it away.
yeah, thanks, Gregor. So I'm really excited that Open Neuromorphic has asked me to give this talk on Spyx, which is a JAX-based framework for spiking neural networks. I'm Kate Heckel. I'm a Marshall Scholar studying in the UK doing artificial intelligence and machine learning. And this is the work that I've been kind of doing for the last 8 months or last year or so. So jumping into it, what is Spyx? Well, it's a lightweight, modular, extensible SNN framework for JAX. It's supposed to be very, very compact. It's not a lot of boilerplate stuff, so you can kind of just get your hands into it and start working with it. Follows the same types of dynamics and approaches the wonderful SNN Torch library. SNN Torch was what I used to try to learn about spiking neural networks, and then use that as inspiration for how do I try to build some of these in JAX. And the reason why I built a new library in JAX and why this was a thing or why I decided to do it, I'll get to. But I built it as part of my master's thesis at the University of Sussex. So for my master's, I was interested in looking at gradient-free optimization of spiking neural networks. And one of the best packages out there for doing evolutionary computation and evolutionary strategies algorithms was written in JAX. So I figured, hey, this would be a good time to learn JAX. And then I looked around and decided that, hey, I think just building some type of small package in JAX for spiking nets would be a good way to learn them, and then also would provide really good synergy for doing these experiments. So the philosophy of the library is we want to train on top of the line GPUs like A100s, H100s, use mixed precision, and all the bells and whistles that we're getting as a result of large language models. We want to use the heck out of them, get 100% utilization, and then we want to deploy cheaply onto neuromorphic hardware for inference so that we can get all of the energy efficiency there. So this is some paradigms think like, well, let's do on-chip learning. My take at it was, well, if we can just push all of the data through the network as fast as humanly possible on high-end hardware, that could be like faster and more efficient for training and iteration and trying to optimize these things. So what is this JAX framework? Why not just use Torch? Well, JAX is really three things. It's just-in-time compilation and other function transformations, which are really handy. It's auto-differentiation, and it's XLA. So you can write code using basically a NumPy style interface in Python, which we're all comfortable and familiar with at this point through different data science applications. And we can take that and have it get compiled down and translated into really efficient CUDA kernels and run it on the GPU. So it's as if we're writing like lower level C type code to run on the bare metal, but it's much more convenient to work with. We don't have to manage our memory as tightly. It's just easier. So the synergy of these three things makes a really good product that Google supports in the open source for scientific computing and other goals and applications. So what does the ecosystem for JAX look like? It's growing. It's got a lot of really neat packages and tools in it. So for example, there's EvoSAX if you want to do evolutionary strategies and optimization. There's BRAX if you want to do kind of multi-body, like multi-joint MuJoCo type control tasks. There's GymNax for more traditional reinforcement learning. There's a library for Gaussian processes if you want to do Bayesian optimization. There's a library for differential equations and like SDEs, ODEs, all that kind of stuff. And the beautiful thing about all of these is that they're all fully just-in-time compilable, and they're all, you can differentiate through them. So if you, in any one of these libraries, you can kind of merge them together, work with both of them, and then just-in-time compile together. And then you get these nice fused CUDA kernels from multiple different libraries. You can just fuse it all together into one deal, send it to your accelerator, and it's really fast. So that was kind of the motivation here for why do we want to build a very lightweight spiking neural network library just in JAX, is we want to, again, leverage this kind of synergy where like we could take EvoSAX to do evolutionary optimization and optimize and train or, you know, evolve hundreds of different spiking neural networks in parallel on a GPU efficiently, and then, you know, try to get better results out of that. So the goals for Spyx, well, was I wanted it to be performant, because if it's not fast, then there's no reason for people to, you know, try it versus staying in the PyTorch ecosystem, which has lots of users, lots of support, lots of documentation, lots of like other previous research to kind of build off of. So if Spyx wasn't performant, then there'd be no point. And then I wanted it to be kind of transparent, hackable, and interoperable. So I wanted the user to be able to look at the training loops, look at what's going on, and then I wanted them to be able to like fully be able to understand and see it, rather than it being hidden behind layers of abstraction where it's harder to then go and modify. And I wanted it to be interoperable, so that way, hey, if I want to do evolutionary optimization of spiking neural networks, the training loop and everything should be about the same as if I'm doing surrogate gradient-based descent methods, where I'm using OptAX and other more deep learning inspired optimizers. I wanted it to be pretty plug and play and have the same efficiency guarantees and benefits. So that was why when you go through the library, there aren't lots of like helper functions that like, here, just give me the model and I'll train the whole thing for you. It's more like, here's a template for how to write the training loops. That way you have full control over the whole process while not being so verbose that it's hard to use and annoying. So Spyx really has it's really three main submodules. There's just a module or a submodule for the spiking neuron definitions. There's a submodule for different functions you would use, like accuracies, losses, regularization. And then there's a function for activation functions. So kind of like where your surrogate gradient functions would live, like the predefined ones that I implemented, and then also some other associated machinery. And then the other two submodules for data and the near are kind of like external things. So data, I provide some pre-built neuromorphic data set data loaders. So that way, if you want to try Spyx and give it a shot, hack around with it for a little bit, see how it works, you don't have to sit and re-implement the whole tonic data loading and loop and all that stuff. There's some out-of-the-box stuff for you to try. But if you want to use Spyx for your research and you want to use it on your own data sets, like by all means do that. You don't have to put things into Spyx data and then like use a specific data loader for Spyx. It's just a convenience submodule. And then near, so there's a recent paper that just got pushed to archive that I was like really glad that I could help contribute to for neuromorphic intermediate representation. So I'll get more to that in a bit. But the idea is like, instead of having all these one-to-one interactions between software tools and hardware platforms, what if there was a common central target we could all write hooks to like import and export from. It would make things a whole lot more interoperable. So Spyx.near is that tooling and that interface for, hey, let's train something on an A100 or an H100 really fast, and then push it to low, like neuromorphic, low cost, low energy hardware afterwards. So that's still a work in progress. But as for like what spiking neurons are implemented, we have all of the usual suspects like leaky integrate and fire, etc. I do include an implementation for some pooling for spiking convolutional networks because there isn't a native and like good implementation of some pooling in normal JAX-based neural network libraries. And there's also some explicit recurrent definitions. So if you want your, an explicit set of weight matrix or set of weights feeding back into a single like spiking layer, there's also implementations for that. So under the hood, what does one of these neuron model definitions or implementations look like? Thankfully, with DeepMind's Haiku neural network package, which is what Spyx kind of extends, it's pretty compact and succinct. So you can see that you really only have to define like an init function where you just set, here are some of the hyperparameters or variables that will help define the function. And then down here in call is where you really just define how the spiking layer acts. Now, similar to SNN torch, the weights and like linear layer is kept separate. So we just use the Haiku linear layer for modulating like the inputs. And then the spiking neuron layer purely handles the state-based processing. So you can see that we calculate like, does the spike fire? And then we decay the membrane voltage and then go to the next time step. In this case, the optional, like the beta parameter that kind of determines like what are the time constants, or in this case, this is the inverse time constant. By default, it's learnable. You can also specify it to a constant across the whole thing. And then it's also got a clamp involved so it doesn't go out of like physically interpretable or good values.
Hey, Kate, sorry to interrupt you there. I had a question. Like you mentioned that the Spyx was based on Haiku. Can you elaborate a bit on because there's also Flex, right? Mm-hmm. Why is it based on Haiku and not on Flex? I think that Flex also had like improved like support by. What can you?
Yeah. So when I was looking to build the library, I was down to choosing between I could use DeepMind's Haiku library or Flax, which was like kind of more Google Brain. And at the time when I was looking at it, Haiku had the best support for like very convenient recurrent neural network definitions and working with them. Because you can see here, you define the neuron model basically in an object-oriented fashion as you would with PyTorch. And then Haiku provides some function transformations that converts it into a functionally pure fashion that JAX really likes. I should have mentioned that with JAX is the one thing about JAX that enables you to get all these really nice features is it kind of forces you to program in a functionally pure fashion. So I went with Haiku at the time because it gave a cleaner recurrent interface compared to Flax, in my opinion. The downside is that Google's shifting their support to Flax. So in like down the road, like in a year or two, like eventually I'll have to migrate the library back over to Flax. And that won't be a massive shift because it'll just change how you write the training loops a little bit, but the same principles and performance like gains are going to stay the same.
Nice, thank you. There's Cameron asking, I also noticed that Flax only supports static unroll while Haiku supports dynamic and static. Is this a big benefit? Is dynamic unroll a big benefit?
So dynamic unroll can be nicer for depending on what hardware you're working with. If you do a static unroll, what happens is JAX generates more code in like the expressions before it sends it to the GPU. So a static unroll will take longer to compile. The dynamic unroll is a little more hardware friendly in terms of it doesn't explode out all the instructions. So in terms of like where that would impact Spyx, the static versus dynamic unroll only affects the length of the spiking neural network versus the time steps of the data. So that shouldn't really impact the performance that much. It'll just increase your compile time.
Cameron also asked about the RAM usage.
Yeah, so yeah, it would increase your VRAM usage a little bit, I think. But the trend with VRAM right now is just exploding. So I would not worry. Like the largest factor in all of your VRAM usage and consumption will be from your data set. And like if you're doing if you're doing autonomous navigation, then your data set's going to be a big chunk of your VRAM. But the static unroll is probably going to be negligible either way.
Nice. Thank you.
Well, if that's it for questions kind of on the neuron definitions, the next thing is just kind of losses and regularization. So a lot of the research I did and tooling I've included in Spyx so far is targeted towards rate-based SNN architectures. So I only have integral cross entropy. So sum up all the output spikes from the last layer, compute the cross entropy, use that as loss. I also have mean squared error spike rate. So you can specify, I want X number of spikes out of the target class and N number of spikes or Y number of spikes out of the non-target classes. And the reasoning for that is I found this was a better loss function to try to target for neuroevolutionary purposes. The thing about purely integral cross entropy is the number of spikes may change, but really only their relative differences is what's measured by the cross entropy. And that was tougher for neuroevolution to adapt to because it was kind of a shifting landscape. Whereas with the mean squared error spike rate, it gave a more stable well of attraction for the like neuroevolutionary optimization to go down into. So that's also an option. And then I have like integral accuracy, and then there is tooling in the library for regularization. So you can set penalties for, I want each neuron to spike a couple of times. So, you want to avoid dead neurons. So there's a loss penalty that you can include for that. And then there's also a sparsity promoting regularization. So you can constrain all of the spikes for a given layer in the network. So that way it's not overly active. So that helps achieve those neuromorphic goals if we want low numbers of spikes that are meaningful. So both of those are included. And with the current Haiku architecture, it's really easy and convenient to work with as well. Then for surrogate functions, I provide pretty much, there's a good number of built-in ones. And then there's this concept of an axon in the library. And really what that is it's just a wrapper that you can plug in a forward function if you wanted to, if you didn't want to have a side step function for some reason. I think if you're doing something with like ANN to SNN conversion, or if you're doing like a recurrent to spiking conversion. But the real big thing is it allows you to plug in any type of function for the backwards pass, similar to how PyTorch has like a dot backwards. So you can just provide even like a lambda function to this axon class, and then it plugs into the network and runs. Or you can use any one of the number of predefined ones. And again, what this looks like in code is so like super spike and sigmoid that are defined in Spyx, all they are functions that take parameters like how steep you want your surrogate to be, and then they return a just-in-time compiled version of that derivative function or that gradient function back to you. So in the case of super spike here, it takes like k, which is how steep do we want the surrogate gradient, and it returns the JIT compiled surrogate gradient function back that gets evaluated. If you can also, in the case of like sigmoid here, like I'm using the JAX and then sigmoid. So say you only have like the forward function of what you want to, or like you don't have the gradient of that function that you want to use as the surrogate. You just have like some step function looking thing. You can also use JAX VMAP and grad to try to turn that into a backwards like surrogate gradient function to apply. So there's kind of like an example of both there.
Sorry, Kate, do you mind explaining a bit what JIT actually means?
Oh, sure. So JIT is that that just-in-time compile functionality that I was talking about earlier. So what that is how there's also like a torch compile, and it's a similar concept. In JAX, you can write code, and then when you call JIT, what happens is there's a compiler that comes in, like an LLVM type compiler that goes in and traces through the code that you provide. And it is able to compute and convert that into an intermediate representation it's in machine learning intermediate representation, or MLIR. And that intermediate representation can then get bound into like a GPU CUDA kernel. Or it can get targeted for TPUs, which it'll have like a different lower, like it'll get lowered to a different target, but it can run on TPUs as well. So this JIT function here, that what's happening is it's taking what it would otherwise be normal NumPy code, and it's converting it into lower level instructions, which then can get turned into like high performance C code. And the nice thing about JIT is that it works on pretty much arbitrary like scopes of code. So you can compose these JIT compiled functions. You can compose a bunch of these functions together, and then it'll trace through, compile it, and then can spit out one giant fused CUDA kernel, or something that'll lower into CUDA, which is wonderful, because whereas in, like, say if you wrote like a QPy implementation of a LIF neuron, and you created then like a Python hook to that QPy accelerated hook, when you call that like QPy custom CUDA LIF neuron, when it goes down into that, it'll run super fast on the GPU, but then it has to come back to the Python interpreter in order to like go to the next step. And you get this back and forth of like hopping back to the CPU, going to the GPU, back to the CPU between each of these instructions. With something like with JAX and just-in-time compilation, it makes it very consistent and regular for, I want to compose all or chain together all these instructions, turn it into one program that gets compiled, send it to the GPU, and have it execute. So you can spend much more time on the accelerator and not having to bounce back between the interpreter.
Thank you. There's one related question to that. So if you anyway have to JIT, or if you can JIT the whole model, do you still need to JIT like intermediate steps?
It's actually redundant to just-in-time compile intermediate steps. It doesn't hurt. It doesn't like help. So say these, like, you don't actually have to return the like this function right here, like the super spike. It could just return like, here's the non-JIT compiled version. Because when you plug that into like your spiking neural network later in Spyx, if you JIT compile the whole model, then everything inside of it gets recursively compiled, and it doesn't, like the whole thing will be the same speed. As a matter of practice, I just decided like, hey, let's return the JIT compiled surrogate function. So if somebody's, if you're using this as part of a loop that isn't just-in-time compiled, you still get the same speed benefits, at least through that section of code.
Great, thank you.
So then it's kind of leading into that with building a model in Spyx. What does that actually look like? So the nice thing about Haiku is, again, we can just kind of stack these layers together as if it were like a TensorFlow, like sequential model, or a torch, like sequential. So the first thing we do is just define our surrogate gradient. So we construct an axon and we'll provide the arctangent function as our surrogate. And then we just have to define a function that kind of builds out the model and then unrolls it and returns the results from the input. So in the case here, there is in Haiku, and I think also in Flax, there's the ability to do a batch apply. So in the case of like the initial linear layer, it's stateless. There's nothing carried over between time steps of the spiking inputs. So we can just apply all of the linear layer in parallel to the input and push it through the GPU first. During experimentation and building the library, I did play around with, well, what if I alternated between unrolling a single recurrent layer and then batch applying the next linear layer and then unroll the next stateful layer. And I didn't really find there was no time improvement at all between like batch applying every linear layer and alternating like the unrolls versus just having like one consistent like RNN core that had the linear layers baked into it. So this was just the easier, like more succinct way to write the stuff rather than having a whole bunch of dynamic unrolls. But you just can plop in. So like this, I imported Spyx as SNN here, and then you can just alternate between like your stateful layers and then your linear layers that act as like the weights or resistances. And then you return the Spyx here is going to be the output. So putting the first layer in the RNN, no, also there is no cost there as well. It's essentially the same, like probably to millisecond scale. This is like a good little way to showcase like there is the capability there. There might be in convolutional experiments, this might be more of a consideration because with convolutions, then it gets more expensive to, like if you recurrently apply the convolutions, it's going to take longer than if you try to just do it all in parallel. But if you try to do it a convolutional operator across the entire batch, it gets much more expensive. So that's like where the trade-off kind of happens. But the batch apply versus large RNN core, like that trade-off doesn't matter much for, it's basically negligible for like just feed forward SNNs that you would deploy on like low power hardware. I hope that kind of covers that. But yeah, so then down here we just call it dynamic unroll, and that gives us the Spyx. So the Spyx output here, that's going to be the outputs from the final layer of your network across the entire time step for the whole batch. And then V here, your voltage, that's going to be the final state of the spiking neural net for like each of the like samples in the batch. So you can go in and see like, oh, what was like the final state of like the first RLIF layer there. And there is a flag that you can switch on in the dynamic unroll if you want to trace or retain all of the intermediate states for the spiking neural network for each of the stateful layers. So there is a way to like save all that if you want to.
Sorry, Kate, do you think you can also briefly explain what the difference between static and dynamic unroll is?
Oh, sure. So static unroll is just, it's going to, because applying the SNN recurrently is like applying a single function in a for loop. So the static unroll, what it's going to do is it's going to just take whatever the body of like apply this function is and copy it out t time steps. So if you're, say you have 128 time steps in your spiking data, when it does a static unroll, it's going to unroll your recurrent neural network application 128 times. For dynamic unrolls, you can, like the default unroll, I think, is just one. So it'll be more of a machine like actual for loop where it's going to iteratively apply the like network one time step at a time. And then with the unroll option, you can kind of flexibly say, oh, I want to do it like unroll the loop 16 times. And somewhere there might be a sweet spot between like performance and compilation time and all of that for like what maximizes the hardware output. But it's not like that's probably not like the major pain point that you want to focus on right away. Like you just tune that to something reasonable. But like the major savings out of Spyx, I'll discuss here in just a second. But
thanks. So
the question is like, why should I try Spyx? Like, why is this new JAX-based library worth looking at? Like, you know, what's the incentive to add it to your repertoire? And the whole reason behind that is this powerful JIT compilation tool, because you can turn literally the entire SNN training loop into a single fused GPU kernel, not just like a LIF layer, not just like, oh, your model application is one like kernel. Like you can push all of your data to VRAM and have the entire gradient optimization, everything, just as a single machine code level program. So this is an example here of like what the output of, I literally took the like super spike surrogate gradient function. This is the the JAXPR for it. So you can see that it takes what was NumPy code and turns into a series of like intermediate representation instructions that can then get targeted to CUDA. You can turn all of your data set shuffling, your like evaluating each batch, computing the loss, updating your, computing, taking that gradient, pushing it through the optimizer, getting your weight updates. All of that can become one fused GPU kernel that just runs on the accelerator and does not come back to your Python interpreter at all. So you get 100% GPU utilization, and you get pretty insane throughputs compared to if you were having to go back and touch the Python interpreter between these like compiled steps. So you can get some, so what? Like, what's the difference between, like, why should I bother with the process of caching my whole data set into VRAM? Like, why should I care? And the reason is because you can train a spiking neural network for hundreds of epochs or epochs. You can do it in minutes. So this is some data from my thesis where you can take a 600,000 plus parameter spiking neural network and you can train it on like 128 time step spiking Heidelberg digit data set, which is a standard benchmark. You can optimize the thing for hundreds of passes in a little over a minute. You can do it for 1,024 time steps. So you can do it like millisecond-ish precision. It only takes 10 minutes, which on like other systems, or if you didn't just-in-time compile, you're talking like hours. Before I did the process of pushing the whole data set, and I was doing like data loading one batch at a time, I was getting like one epoch every like 30 seconds. And then after I pushed everything to VRAM, I could do 300 epochs in 30 seconds. So it's like a pretty, it seems pretty insane. Like I went to my advisor and said like, yeah, I did this change and now I'm getting like 12 epochs per second. And he's like, are you sure that's right? And yeah, like you're very right to also be questioning right now, like Spyx is new. Can I trust that you're actually just getting hundreds of epochs in minutes? Like this seems pretty absurd. But going back to that neuromorphic intermediate representation paper, which is on archive, and definitely please go check it out. It was some great work by the community. Spyx, you can see through this similarity table, which the objective or this figure is showing a bunch of different neuromorphic simulators running a spiking convolutional neural network and checkpointing its activity at the end. Is that Spyx's final output is similar to the outputs from Lava, Nengo, Norse, SNN Torch. So it's actually learning a real spiking neural network in the span of like a couple minutes. It's not just churning through like cached data and then not actually learning anything or generating a real network. It's actually doing so good question of if your data set is over several terabytes, then yeah, you're not going to be able to fit all of that into like a single accelerator's VRAM. That there are some tricks that I have implemented for like one thing, like a hack you can do is take your entire data set and then compress it along the temporal axis. So since each spike is only a 1 or a 0, we can take the entire data set and scrunch it. So that way we fit 8 spikes into a single 8-bit integer. And then as the training loop's going through, every time it goes to a batch, you can then unpack along that time axis and then run through it as like a full like 128 time step simulation. But the rest of the data set is still kind of zipped down in this like 1/8 size format. So that helps you if you're working on like a A100 or an H100, or as we get to hopefully like GH200s or like even higher VRAM systems for trying to do this research. You should be able to hopefully compress like 100 plus gigabyte data sets down and then still be able to run, you could squeeze 8 gigabytes into 10 gigabytes for the most part, or like that should help address that. If you're really into like massive data, then this is probably not as much, you'll probably struggle to compress that down. But in terms of like, how can we find like better surrogate gradient functions or better like architectural motifs in spiking neural networks. I think Spyx offers a great opportunity for, let's train this on like practical benchmark data sets, but let's do it really, really, really fast. So that way, when we scale up to like, say, a multi-terabyte data set, we at least know that like the underlying, principles of the architecture that we're training is going to be sound. So we're not like waiting until the end to be like, oh, it worked or it didn't. I have not played around with the IBM 128 dBs gesture dataset yet. If somebody were to do that in a tutorial, I would be very happy to feature it on the GitHub repo. But I do have example notebooks for like MNIST or like NMNIST and that. So I'd be happy to put those up and help share those as well. I know that the DVS gesture, like there are some very large data sets out there. So that would be really great to try to run on a benchmark. So the catches with Spyx, we've already kind of talked about, like what are some of the constraints. Obviously, if you have a massive data set and say you don't have like an 80 gigabyte VRAM accelerator, so you only have like 24, then you're going to be somewhat constrained on VRAM usage. I was able to do a lot of like the spiking Heidelberg digit data set research on my laptop with only 6 gigabytes of VRAM. So it's not the end of the world if you don't have an A100 or an H100. But the scenarios where Spyx probably isn't the right fit, especially is if you need a dynamic computation graph. So if you're trying to build out a spiking neural network like one neuron at a time, or if you have like reasons why your data and stuff would change shapes in the middle of computation, then Spyx is not a good fit because you can't compile that with JIT through JAX. So that's an example where it's probably not the right fit, and like a PyTorch-based framework would be better. Also, Spyx is very deep learning oriented at this point. So you could try, if you want to build your own or put in like an Izhikevich neuron or Hodgkin-Huxley, like you can, or Hodgkin-Huxley, geez. You can define it yourself and like play around with it in the framework, but that's just not kind of what I was aiming for with the library. But it's, it's supposed to be hackable and it's whatever you want it to be. And then like computational neuroscience applications kind of rolling in that, like having non-trivial connections between layers, like non-adjacent layers, having like feedback loops and stuff would probably be kind of ugly and harder to implement in Spyx compared to something like Nengo or Brian or these other more neuroscience focused libraries. So Spyx is really just kind of a deep learning, like SNN, go really fast. That's the kind of gist of it. Residual connections. Yeah. So if you want to do residual or like skip connections, there is a haiku function at the moment that allows you to include, there's like RNN core with skip connections. I haven't played around with it because I was still trying to figure out, I was concerned about the issue of like the skip connections might like, they would skip in between the linear layers and the like stateful RNN layers. And whereas I feel like you would want the skip connections to go like between the stateful and linear layers as like a single unit. There's probably a way to shoehorn that. I just haven't played around with that. As for like, if you wanted a connection from like layer 5 deep in your network to feed all the way back to the beginning, there's a way you could probably construct it. It's just that it's not going to be the prettiest. I mean, if you can do it in Torch, you can probably set it up the same way in Spyx. It's just not going to be elegant either way. Whereas like Nengo has like easier. I mean, if you're like using a GUI or something, it's probably easier. But like if you would be able to define it, or like some like connection patterns that you would do for like a traditional artificial neural network in Torch or JAX, you can make it work for Spyx. I just haven't played around with any like crazy architectural configurations, so I can't provide as much offhand knowledge for how that goes. But so as for like what's next for Spyx, there's a lot of things that are possibilities and would be fun to do. It all just kind of depends on what the community interest and engagement is. So it's very much an open book. I need to finish like the tooling for exporting models from Spyx to this neuromorphic intermediate representation. So that way it helps solidify the whole goal of train at high throughput on high end accelerator, deploy on like high efficiency, low power accelerator. Tutorials I need to work on. That's like something I'm aiming to improve, and temporal coding features or walkthroughs would be good as well. Adding conversion for ANN or ANN SNN conversion examples and machinery would also be a goal, and then like reorganizing the data loading a bit. Aspirationally, I definitely need to add or would like to add some more like software engineering things like test cases and like type checking on all the things. So like increasing and improving the user experience. And then I think there's lots of like really interesting research like avenues for like doing large, like Spike GPT type models or like state space machine inspired models on like doing them within Spyx. So you could try to leverage like large accelerators and try to go fast in like a different kind of context would be fun. And what I'm saying, like going fast, like the PyTorch libraries are also really good. Like they also have the ability to compile. It's just that the Torch compile is not at the same state as Jack's like JIT compiling is in terms of like what you see is what you get. But I'm not a Torch guy. I do not program in Torch. So like other people may have very different experiences from or on Torch than what I personally know.
On that, I have a question. Like, do you think if one would like functionally program a clean SNN library in PyTorch, you think there would still be a difference in performance between and then Torch compiled it, obviously? That's hard to say, I guess.
Yeah. I mean, I can't make an intelligent statement on that without. I don't know the Torch internals. Like, I mean, I'm sure there's lots of very smart people working on like Torch Dynamo and all of that compilation. I'm not sure. Yeah, I mean, it's a possibility. I'm not going to rule it out.
Sure. No, I understand.
So
makes sense.
I'm just like Spyx is just another like it's a new tool. It's like another opportunity,
But the fact that, as you said, like in the beginning, that JAX forces you essentially to do the functional programming part, like this is not the case in PyTorch, and that's why a lot of the SNN frameworks then don't work with PyTorch compiled or don't benefit from it. So
I think I haven't played around with Torch compile. I know it is more finicky. I think that there probably is a way to restructure some like the PyTorch work to be maybe more amenable or like easier to work with the compilation process. But I think at that point, like SNN Torch and like Torch-based frameworks are great because they're more flexible, they're object-oriented, they're like very user-friendly to pick up if you've learned or grew up in Torch. Spyx and JAX, like there is a learning curve, like you have to manually handle your RNG state. Like, there are like JAXisms that can be a little annoying to like start picking up with, but then at least in my experience, once you get used to them, you start to enjoy and like that aspects of like, oh wow, like, yeah, I mean, it is annoying to like have to manually pass the parameters and be careful about that, but at least I know, like, I can see what's happening with the random number generation. It is perfectly reproducible every time. There isn't like a hidden seed somewhere. Like the side effect free programming is like, once you get used to it, it's enjoyable. So it's not like always a painful process once you get accustomed to it, but.
Very nice. Do you think you're going to show us some of that?
Oh yeah, just in a moment. Just we're on the like last slide or so.
Perfect.
But yeah, just like other cool things. So like the Brax library, which is like Mujoko. I think that there's a whole lot of research that could be done with. If you're interested in neuromorphic control, now you have all these spiking neural network primitives. You have a fully just-in-time compilable and differentiable like physics simulator, and then you can like through the design kind of merge these two together synergistically and then push them to GPU and have it run. And then there's other things that are possible with like using complex autodiff for phaser networks. And like, there's lots of ideas that I don't know about that the community is interested in. And the ideas with Spyx is just be as open and as modifiable as possible. So that way it's not forcing you to do anything. so you can do with it what you like. So there's a number of issues open on the GitHub. Contributions and stars are welcome. Otherwise, if you're interested in trying out Spyx, it's on my GitHub. There's documentation for it that I got some help like initially configuring. And there's some like example notebooks you can go through. So if you want to try it, you can do things like implement your own surrogate gradient or try your own custom neurons. So there's a notebook on here's how you can do neuroevolution for cart pole if you're interested in like spiking neural network for controls. And if you're really inspired, you can try adapting one of the notebooks for your own data. And the nice thing is for like the spiking Heidelberg digit data set, this will run in Google Colab. You don't need a whole lot of VRAM to make this stuff work. So, but that's all I have. So if there's any other questions, I'm happy to answer them. And thank you all so much for your time. So.
So I think I don't see any more questions for now. So I think
the notebook run through.
Do you have is this publicly available? Can people step through this as well, or?
Yes, this is the same surrogate gradient tutorial that's on the like docs page.
Yeah. Okay, I will put that here as well as a link. And so what is your plan now? Are you gonna step through this notebook to like the tutorial with us, or?
Yeah, that's kind of the I'll run through it and just kind of like dissect some of the like whole training loop, and then we can see it run in real time. So
cool. Maybe there is two questions that just popped up. So one is by Jens. Do you have any plans on extending the Neuron Zoo?
Yeah, so I tried building the library in such a way that it's easy to implement your own. I don't have any, like, there's lots of Neuron models out there. If anybody has one that they think is missing and would love to add, please, by all means, submit a pull request and I will throw it in. I am very open to like anything.
And I guess
there's nothing like I personally am like I want to throw in at this moment in terms of like, oh, I didn't get around to that and have yet to do it. But I am extremely open to including as like anybody's suggestions, code, etc. So
there's also another one about plasticity, new plasticity or learning rules. I guess just a matter of implementing those.
Frankly, I'm not experienced and as knowledgeable about plasticity-based learning rules. If they are, I'm not sure how to go about implementing them. But like if there were to be a notebook that shows how to do it or something like that, like I haven't looked into them yet. I'm very open to any ideas. So
cool. There's one more question by Jason about what are some of the key syntactical differences between PyTorch and JAX during training, but I think we're about to find out, right?
Yeah. I'll kind of walk through the process and stuff like that. So
great, thank you.
So this is the surrogate gradient tutorial. You can find on the Spyx documentation on the read the docs. It's this link right here. So it's the same notebook. We'll see if this loads. The internet is, but it's the same notebook. So it's publicly accessible, and you can download it, throw it into a Google Colab, and play around with it on your own time if you'd like. So you can just download the IPy notebook right here and put it into the Colab. I have it here running on my local machine, which is a Dell XPS 17. It's got a NVIDIA 3060 in it with only 6 gigabytes of VRAM. So this, like, we're not like running on any crazy hardware here. So we'll just import the libraries. So we import Spyx, and like the NN module is like SNN. We import JAX and its associated stuff. We import JAX mixed precision specifically. I can zoom in if it's.
Yeah, that would be great. Thank you.
Yeah.
Maybe you, yeah, perfect. I think you can deactivate the Explorer if you.
Yeah, I'm just trying to. Gosh darn it.
I think it's fine.
This is as close as we'll get, I think. Or that wasn't it. Gosh darn it.
I think if in my VS Code, if I pull the separation bar between the notebook and the file explorer just to the left, then it does it.
Yeah, this is it's not VS Code. It's a different tool that just looks a lot like VS Code. So I guess
okay, good. No, it's good. We can see it.
It's fine. That. But yeah, so we import Jax or Jax NumPy is JNP. JMP here. This is Jax mixed precision. So what this library is it provides us with automatic precision tooling. So the nice thing is on like an A100 or an H100 or a TPU, we can specify, let's use like half precision floats. And then we can get not only memory savings out of that as well, but we can also get computational speed ups because we're using like the A100 and other AI accelerated GPUs have higher flops for low precision data types. And Jax TQDM, this is like pretty progress bars. We import Haiku, that's kind of the base that Spyx sits on top of, and then we have Optax, which is our optimization library that's native for. So it's the gradient optimization library for Jax. So we import that, and then some other matplotlib stuff, and then just a quick example of here's like how we generate. If we want to look at the JAXPR, the expression that's kind of like the intermediate representation output by a JIT compiled function. We take like the super spike function here, and then we see that it produces this JAXPR of, it takes in an array of a certain shape and then does like the single static assignment for like, here's the different operations that compose the super spike surrogate gradient. So this is just like a little demo. This is where we can specify like a policy. So we can say like, hey, do all of our compute, store our states, weights, do that all in half precision to save memory space. And if we're on like an A100 or an H100, we get some performance boosts out of that as well. The nice thing is you just have to set it here once, and then it cleanly does that in the background, so we don't have to worry about it. So that's a plus. We'll load up the spiking Heidelberg digit data loader that comes in with Spyx as an example. So what we'll do here is this is a batch size of 256, and then it's 128 time steps and 128 channels of data. So each of these will come out as like a square raster right here. So what this data loader is doing in the background is it loads in the entire data set to CPU, concatenates it into a number of batches by batch size, by number of like time steps by data array. And then it squashes it into this huge tensor. And then it will compress it along the time axis and push it to VRAM as a single like Jax NumPy array. And the reasoning for that is so that way we can push all of the data as like one array to VRAM, and then we can write our whole optimization loop off of it, compile it all, and it'll run as like a single unit. So the data loading does take like a hot second, but that's just because it's running through the CPU. If you don't have the data set already downloaded, the data loader will pull it down or pull it into the Colab environment for you. So there isn't much need to worry there. Come on.
So what is it doing here under the hood? So it's preparing clearly. It's loading all the data
it's
from
just
the files.
Loading the data set. I think
binning them to the right time steps, number of time steps, and then stacking them.
Yeah. It pulls out, like rasterizes all of the events, stacks them together as one tensor and pushes them to the GPU.
Sounds good.
I forgot to put my computer into performance mode, so it's probably running on like a flimsy efficiency core for like the last minute, so I apologize. But then we'll initialize like the data loader here that I have implemented. Like it'll provide like, here's a training epoch, and then you can shuffle that. And then there's also like validation and testing. These are just like some nice abstractions for rather than having like a really big block of code for like, here's the data loading. But you don't have to, like if your data set isn't in Spyx data, like really do not worry about it. Like you can write a data loader that's probably better and more understandable than mine. Because mine are just kind of monolithic in the background. But this is an example here of like one of the Spyx rasters. So you can see the speech outline here. And then, so Y is our set of target labels of like which digit is being spoken. And we can see that it's of shape 25 by 256. So it's 25 batches of 256 samples each. So then we come down here to define our spiking neural network. So we have like a linear layers, we have leaky, integrate, and fire neurons with triangular activations. And then we have a final leaky integrate layer, which just gives us a way of, we just measure the output voltage of the like last layer rather than like counting spikes. You can have a leaky integrate and fire as your last neuron. It's not like a, deal breaker. And then we just call dynamic unroll and like return the spikes in the voltage. So then this cell here below, we call hiq.transform of this like constructor function up here. And then we also call or chain that with hiq without apply RNG. In the case of like our classification problem, there's no stochastic elements to our spiking neural network, so we don't need to it'd be annoying to have to pass in a random key every time when we're not using random keys. So after that, we just init our spiking net, and it gives us the parameters. So we'll run this function here to define our constructor, and then we'll initialize our parameters. And this will just take like a hot second, so 2.5 seconds just to generate the parameters. And these parameters are stored as basically, it's called a pie tree, but it's basically a nested dictionary of like, here's the parameter name and here's the associated like JAX NumPy array. So then the next thing is we get to like the body of our gradient descent. Like this is our main training loop, like body here. So we pass in like our SNN object, its parameters, our data loader. Then we specify like the number of epochs we want to run and the schedule. So from OptAx, we're going to use the Lion optimizer. It's similar to Atom. It's just a little lighter weight. I found it worked pretty well and I like it, so I stuck with it. And from that, we initialize our optimizer, and then we also just save a separate name of our parameters to not get them mixed up scoping wise. So the first function we're going to define here is a network evaluation. So this essentially just takes in our weights and then our X's and Y's, so our like spiking data and like what the targets should be. And all we do is like apply the spiking neural network to the data, record the outputs, and then compute the integral cross entropy. That's all this function does. And then we'll just in time compile that. And then one of the beautiful things about JAX is part of its function transform or set of function transforms besides JIT compilation is its auto differentiation. So we can just call jax.value and grad on this eval function. And it gives us back this function that I called surrogate grad. But what this does when you call it is it'll provide you like, here are the like output, here's like the actual like loss values that are the outputs. And then it also gives you the gradient that you can then provide to the optimizer and apply to the network. So next we define our training step. So this training step has to have like there's a specific structure to this that I'll get to. You provide like the state. So kind of like the carrying over value of like each step of training, what's the current like optimizer and like parameters. And then we have data, which is like our big data array that we're kind of like scanning over. So like, remember this data, which is our big X array of spikes, has a shape of like number of batches by like, and then it's data. So in this training step function, we unpack our parameters and state, we unpack our data. So we have our like events and targets that have a shape of like 25 batches by like data and targets. For the events, we then call J and P, like we do these unpack bits. So this is what I was alluding to earlier of if your data set is large, you can compress it down along the time axis. So that way you're saving like 87.5% of your storage because you're storing 8 bits in every byte this way. And then when you go to like perform inference or like evaluate on a single batch, you just unzip that single batch. So you're only having like, 256 samples stored at like full spatial precision at any one time. So you can save a lot of memory this way. Then we call our surrogate grad function that just takes our parameters, events, and targets and gives us back the loss and the gradient. Then we pass these to our Optax optimizer, and it gives us like the updates that we're going to apply, and then also the new optimizer state for like momentum and such. And then the new state that we're going to return out of this will be like the new like updated parameters and the new optimizer state, and we're going to return that plus the loss. And the reason why we return the loss is because we're going to keep track of this loss as well, because then we can show at the end like, oh, here's our loss curve over time. And then we do a similar thing for our eval step, except we just call like compute the accuracy, compute the cross entropy, and then we're going to track those metrics and then we don't have to worry about updating the parameters since this is just like a validation like pass. So now that we have these two functions built, one that does like for a single batch, like compute the gradients, update them. And we have a function that for like a single batch of the like validation data set, just compute the metrics. We can then combine these two together. So what we do is we define a third function. And I know this is getting a little like, kind of turtles all the way down here, called epoch. And then what we do is we have like a state for that. And then like the numbers are just like which, iteration. And what we're going to do for like the epoch is we just keep passing our like SNN parameters through this whole chain so that they keep getting updated like over the course of time. And then also our optimizer state, we need to persist that and push that through like each pass of the data set and then each batch. So then we shuffle our training data set each like epoch, so that way we're not training in the same procedure over and over. And then here's where we use a tool from JAX called scan. And what scan does is it takes a function and it takes us like an initial state and then an array of data. And it takes that function with that initial state and just applies it iteratively across that whole data. So what happens here is we are basically getting a fully compiled for loop that takes our spiking neural network and applies it to each batch sequentially while computing all the gradient updates for the training set. And then we go down and do that later or below on the validation set as well. And then we can basically provide those parameters back out. So then when we scan this whole, we run this epoch function using another scan, what's happening is like all of this gets turned into one fused CUDA kernel that will sequentially go through, like shuffle the data set, apply our spiking neural network on each batch sequentially while computing the gradient updates, validate it, go back, start again, like keep updating the gradients and optimizing the network and so on. So we just need to run this cell so that way we like define this gradient descent function. And then we have a similar like test gradient or like a test function that has the same philosophy of we have a like test step that we then scan across our testing data set that we cache to the GPU. So we run that. So scan does the compute, yes. So when you call scan, it'll go through and run this. Yeah, that's correct. That scan applies the compute. So now when we come down here, this is our function that we're going to run that it'll call this big gradient descent training loop function, which inside of it has a scan of like the epoch function, which the epoch function then contains two different like scans of like, here's how you do a like pass over the training set, and here's a train over the validation set. So this is where we're really like, all these internal JITs aren't necessary because like the scan, like a scan compiles everything inside of it, just as a heads up. So like, for example, what is not compiled is just like this initial setup. Like this isn't compiled. What is compiled is everything that happens within this epoch function. So all of the like training gradient updates, all of that stuff, everything all the way down in there, fused into one kernel runs. So then when we go down here to run it, you'll see this clock starts ticking, and it'll take about like 10 to 15 seconds maybe, because what it's doing right now is doing all of this just-in-time compilation. And now we can see that the progress bar hits, and we're getting, 14 iterations per second. And each one of those iterations is a full pass over the training set, computing these gradient updates, and then a full pass over the validation set, computing the validation metrics. So what we're doing right now is we're running 300 epochs over the entire data set to train the spiking neural network in the span of 23 seconds. So that's, it definitely is kind of involved to build out like training steps, validation steps, cache the whole data set, scan it, make the shapes play well. Like it does take upfront engineering, but then you can get the payoff of, I just trained a spiking neural network in 23 seconds that usually takes much longer to run when you're streaming data from the CPU and not fusing the whole thing. And our performance, you get 92% validation accuracy. Here's the like training validation, like loss and accuracy curves. And then we'll evaluate it. The accuracy will be, it's not bad. 76% isn't state of the art by any means on SHD, but for this tutorial, I cut out some of the other features of Spyx. Like there is a data augmentation tool in Spyx that rolls, like you can randomly jitter and shift the speech waveform, spike rasters around to like help with regularization. Like you can include the penalties for like silent neurons or like overactive layers. Like you can tune all of those other things, and then you can use other optimizers from Optax, and you can include like dropout or batch normalization or gradient centralization. There's lots of other like techniques that you can throw in to get your performance from this like into the 80s. But the key takeaway is just we trained this neural network in 20 seconds and it gets to like, a good number. So like it's actually like a working example. And then here's like a confusion matrix that we can print. But this is like and then again, this is running on like a 6 gigabyte VRAM GPU. So this is something that like you don't necessarily need top shelf hardware in order to get started with Spyx and use it. But okay. That's about all I have. Definitely happy to chat and discuss, but
there was super interesting demo. Thanks a lot for that. Like we have some more 20 minutes more if people have some more questions. Like just post them in the chat and I'll bring them up. So like in terms, I have maybe some more questions. Like also what Cameron alluded to earlier. Like, do you think it's easier for some specific learning training methods, such as like if I wanted to calculate gradients based on the spike timings, do you think that would be easier to do in Spyx rather than in PyTorch? Because PyTorch it doesn't play well with time steps, let's say.
So if you have a model that's like really time intensive, I can say that the like scaling of Spyx is linear with time. Like it has very good linear scaling for temporal resolution. I haven't played around with like time-based spiking systems, so I don't know very good specifics on like, oh yeah, this would be a perfect fit using this functionality within JAX to like isolate spike times and all of that. What I can say is like, if you want to do like Spyx right now, like is very much architected like, here's a really great tool for rate-based spiking neural networks. If you want to do surrogate gradients, it has first-class support for surrogate gradients. If you want to do neuroevolution, it has really great support for neuroevolution and like gradient-free optimization. One of the other notebooks on the like docs is for training a spiking neural, like a cart pole balancer using neuroevolution. So like you can evolve, and this is like one of the advantages of Spyx that, or in JAX that isn't as present. There isn't as much evolutionary computation frameworks in Torch, for one. And for two, another function transform that JAX offers is called VMAP, which is how you can take a function that's like meant for one thing and apply it across a whole array at once, and it auto-vectorizes it. So for the context of evolutionary computing, what you can do is, I'm trying to find the exact spot. You can have a population of 128 spiking neural networks and then have a vectorized environment of like, here are 128 ants in bracts, like four-legged walkers. And what you can do is use VMAP to just take that environment for a single ant, apply it, and then apply all 120 of your networks to an ant, like a separate ant simulation, and then do like evolutionary optimization that way. And that's something that you really can't get the same ability in Torch in terms of
that makes sense.
vectorization. So,
and that plays very well with TPUs as well, I guess.
Yes, I need to do more experiments on TPUs, but the JAX is a Google framework and has like TPU first class support for. If you're working with TPUs specifically, there are some other like tricks for like, how do I wring more performance out of them, and that's where you get into like having tile set. You want your data and everything to follow multiples of 128. So
that's why you chose these number of time steps, for example, and like
yeah. So like this is all on GPU. At some point when I get around to it, if I can get Google Cloud to play along and actually allocate a good TPU,
they should sponsor you, man.
Yeah, I tried doing the TRC like research cloud, but then I like ended up running out of time and couldn't allocate a proper. Like it was just I couldn't get a TPU allocated.
Sure. And talking a bit, sorry.
Go ahead.
Now talking a bit about like like using like the Spyx layers, like seems relatively intuitive. I mean, what about the tooling around it? Like when we think like talking data loaders and optimization. So for example, Cameron asks here about like you're using a separate library for that. Like what's how do you see that?
Yeah, so I think there is like a stub for optimization within, like I think JAX has a built-in stochastic gradient descent. The reason why OptAX, for example, is because it's got a large selection of modern like optimizers used across deep learning, like Lion, for example, which is like well benchmarked and looked at as well. Like all of these, like it's just, that's the library people use for training like other deep neural networks in JAX. Like OptAX is the most popular prominent one, so that's the one I went with. But yeah, the options for optimization, you have OptAX. If you know of other optimization libraries, like Spyx is meant to be as like non-committal towards one or the other. That's why there's no like hard-coded training loop that everything's hidden away from you. It's just very much like, here it is, like plug in what you want. Like, I mean, it's the flexibility is demonstrated by like, you can use OptAX or you can use EvoSAX and do evolutionary optimization, and the differences between the loops are minimal. I need to push one of the other like evolutionary optimization notebooks up, but yeah, you'll be able to see that it's literally the differences are just take out OptAX, plug in EvoSAX, and the rest of the whole like nested training and epoch loops are unchanged. So
would you agree that the ecosystem is just not as mature yet, but at some point we'll see something like JAX Lightning, like the equivalent of PyTorch Lightning, that structures your code and like abstracts away some of this, well, I'm not sure if it's boilerplate, but some of this, just very verbose code.
I mean, possibly. I think the big thing will be some type of the multi-node JAX at the moment is a little more intensive to write because of handling like the parallel mapping and stuff like that. That's not, admittedly, not as clean at the moment. As for like a Lightning equivalent, I'm not sure. Maybe. Yeah, I mean, it's just the trade-offs you make. Like, if you want something that's like faster to write and like hides more of the stuff from you, then it might be harder to optimize. With Spyx and JAX, what you see is what you get, and like it will compile and run fast. I just elected with like how I structured. Like I could have just had or like sequestered away most of the training loops and like stuff behind like a trainer object that you then pass stuff to. I just thought that that would be.
Apparently, there's now JAX support for Keras.
Oh yeah, I have heard about that. Yeah, I don't know. Like, Keras definitely would be a good option. I don't know if I'll move. I'd have to look into like moving Spyx into a Keras format, but that could be a definite option as well if people are interested. The reason why I like kind of pinned it to JAX was just because of the hardware support and everything. If people like, yeah, I mean, because like if I were to move it to Keras, like now you do have multi-framework backends. So like if you wanted to do Torch again, you could, but at that rate, you should just stay with SNN, Torch, or Norse, or like something with more documentation and user base. But yeah, the tough thing is just getting that multi-node scaling is just harder to program at the moment. But I'll have to look at how Keras handles multi-GPU with JAX. But
makes sense. Apparently, the Keras backend is a pain, but easy for the user.
Yeah, I'll definitely have to look into it. Exciting stuff.
Talking also briefly about the data loading. So like if people now want to experiment with their own data sets, like how involved is this implementation that you have now in Spyx data sets?
Sure.
How difficult is that?
So it's really just like writing the data loader for like a torch-based library. I'll pull up what I have. So for example, I'll scroll down to like spiking Heidelberg. So like I have a rastering function here because you have to convert like the events into like a square raster. And then really the data loading is just like, well, what do you want your batch size and validation size and observation size, all that stuff. Then it's built off of Tonic, and it uses Torch Vision to help with some of like image libraries, like for MNIST. But for SHD, it's just using Tonic behind the scenes to load the data sets. And then I use sklearn to generate like a train test split out of the data set. And then I use, right now, I'm reliant on Torch data loaders to like subset out the train test splits. And then like I iterate through, collate them into like lists of all the data, and then compress those into, like I tensorize them and send them to GPU. So like if somebody wants to write their own, like you really just, whatever you need to do to like load the data up in Tonic, just pull the whole data set into CPU RAM as a list, then convert it to a JAX NumPy array with like uint8 data type. And then you just compress along the time axis to be using like pack bits or unpack bits so you can save VRAM.
So I guess my point is that this code that you have implemented here is somewhat generalizable, like generally usable for other data sets as well, right? Because you essentially load all the data, you split it, and then you shape it in the correct form. Right?
Yeah. So if you wanted to, you could.
This could be somewhat abstracted if people would
I
reuse
could
it.
convert or add in like an abstract base class that people could then extend and like implement the 3 functions. That would be a good design choice. My other consideration is just pulling like the data part out of Spyx, like these data sets, so that way it's not like you're not necessarily needing to pull in or download Torch Vision and then play around with like getting Jax and Torch to work in the same environment, which sometimes can be a pain, sometimes not. My goal was like minimize the amount of dependencies for the library, so it's just as easy as possible to throw into an environment. But yeah, I mean, the same template of these things works generally because it's just use tonic to load the data set, turn it into a tensor, and then there's like the functions that you call like for like train, val, and test, like epoch, that just spit out the data. They all basically just provide the same like view of the data, except the train version performs shuffling each time for you, so that way it's not like repeating the same exact ordering of the data. But I found it more efficient to randomly shuffle the data set once per epoch in memory than it was to draw random samples from the memory each batch, if that makes sense.
So you rearrange it in memory once rather than when you say
so yeah, what I'm saying is before I each pass over the data set, the first thing I do is reshuffle the whole training set so that it's a different ordering of batches by samples. Like the whole thing gets rearranged. Like all of the samples get rearranged. And then I just scan over that like one pass and then I rearrange the whole thing. The other option that you could do that I tried was you have the whole data set sitting in memory, and then each batch you're just randomly sampling 256 samples from the whole data set. But that was much worse for performance in terms of you're missing out on data locality and all that stuff. So you're going to be slowing yourself way down. So the good pattern is just randomly shuffle the data set once per epoch and then run over the train set and then reshuffle it and then run over it again. But
very nice. I think but currently there's no more questions. So if people wanted to get involved, or like people wanted to play around with it, what would be some good resources to look at? Where can they get started?
Yeah, so resource-wise, just the GitHub repo and the associated read the docs has like some starter notebooks, templates to go in and play around with. I'm still working on improving the documentation. That's a continuous thing. But really, yeah, you can run this stuff in a Google Colab. You can run it on like a gaming laptop with an NVIDIA GPU. You can run it on like anything with 6 gigabytes of VRAM is enough to run the like spiking Heidelberg example. So I'm definitely happy for contributors as well. Like I have issues listed on the GitHub, as like sample ideas, but I'm extremely happy to welcome other, suggestions and ideas. And if people think like, hey, I don't agree with this design pattern, I'm really happy to get some advice and feedback, because like I just wrote this and was trying to figure out what right looks like as I went. So if there's something like, oh, I think we should think about this differently, I'm definitely happy to have that discussion, like be very open-minded to that. So. And
if they wanted to get help, I guess they can post on the O&M Discord. There's like a Spyx channel that you have as well, right?
Oh, yes. The Open Neuromorphic Discord has a Spyx channel that I monitor. So if people have questions or ideas, that's also a great place. If it's something like a bug or like a longer term issue, like definitely ping the Discord channel and also throw up an issue. So that way it's like doubly documented and visible. But yeah, definitely happy to have discussions in both Discord and on GitHub. So
great. You want to say anything else, or otherwise? I think
I just would love to thank Open Neuromorphic and the whole community again, like Jason, Jens, you, Gregor, and everybody else who helps like set this stuff up and make it run, because definitely, I wouldn't have been able to get involved in the community and like really tear into this stuff the last half year or so if there wasn't all of this great like open community that was happy to collaborate and chat. So just really thankful again for the opportunity to come talk, and hopefully people, found this interesting and want to give it a try. So I'm always happy to talk.
Really, really great talk. Really enjoyed that. Thanks a lot. Really nice tool. What you did in 8 months working on SNNs is amazing. So I hope, the community will pick it up as well. And thanks again for the talk. And I hope to see you soon on Discord or GitHub or in real life, hopefully.
Yeah, thanks again.
Cool. Thanks a lot.